Imagine standing less than 1,000 kilometers from the South Pole and finding no endless ice, no exposed rock, and no penguins huddled against a blizzard. Instead, the ground is dark with wet soil. Rivers cut through low forests. Ferns crowd the understory, conifers rise above them, and flowering shrubs grow in the shade. For part of the year, the sun never sets. Then winter arrives, and the same forest sits through months of darkness. That was Antarctica before it froze. There was not one single green Antarctica. The continent changed repeatedly across tens of millions of years. Around 90 million years ago, during the age of dinosaurs, temperate rainforest grew close to the South Pole in what is now West Antarctica. Fossil soil recovered from beneath the seafloor still contains tangled roots, pollen, and spores from that vanished landscape. Much later, around 52 million years ago, coastal regions of East Antarctica supported another rich forest world, warm enough in some lowlands for palms and other frost-sensitive plants. The strange part is that Antarctica was not sitting somewhere near the equator and slowly drifting south. It was already in the polar region. The continent had not misplaced the South Pole. So the real question is not how Antarctica reached the cold. It is how land beneath a polar sky could support forests in the first place. The answer begins with a planet that worked under a very different climate setting. During the warmest parts of the Cretaceous and early Eocene, atmospheric carbon dioxide was far higher than today. That trapped more heat, but the effect was not limited to hotter tropical afternoons. Warm oceans moved energy toward high latitudes, winters became much milder, and permanent ice had little chance to spread across the continent. Along the early Eocene coast of what is now Wilkes Land, evidence from fossil pollen and chemical traces preserved in seafloor sediments suggests that winter temperatures may have remained above about 10 degrees Celsius in some lowland areas. That does not mean every part of Antarctica felt tropical. Inland and higher ground supported cooler temperate forests, but even there, the landscape was wooded rather than buried beneath kilometers of ice. The biggest obstacle was not necessarily cold. It was darkness. Plants near the pole still faced a long winter without sunlight. They could not photosynthesize through it no matter how warm the air remained. Some likely slowed their growth, dropped leaves, or relied on stored energy until spring returned. When it did, months of continuous daylight allowed an intense growing season. And those forests were not empty scenery. They were the foundation of an Antarctic ecosystem that would look almost impossible on the continent today. Dinosaurs moved through some of these forests during the Cretaceous. Their remains are rare because exposed rock is scarce, and most fossil-bearing ground is hidden beneath ice. But enough has been found to show that Antarctica supported real land communities, not a few desperate animals clinging to the coast. Armored dinosaurs lived there. So did long-necked herbivores, small plant eaters, and predators. Some species may have remained through the dark winter, while others could have moved north as the seasons changed. Fossils alone cannot tell us exactly how much they migrated, but any animal staying near the pole had to deal with a yearly rhythm unlike anything in most dinosaur habitats. For months, summer light would keep plants growing and food relatively abundant. Then the sun would disappear. Temperatures in some periods were still mild enough to avoid deep freezing, but darkness would shut down most fresh plant growth. Herbivores had to rely on tougher leaves, bark, stored vegetation, or whatever remained available. Predators had to follow prey that was becoming harder to find. This did not make Antarctica a tropical paradise. It made it a polar forest with a surprisingly gentle climate. After the non-avian dinosaurs disappeared, forests continued to cover large parts of the continent. Early penguins swam along Antarctic coasts, including species far larger than most penguins alive today. Marsupials and other small mammals lived on land. Fossil wood, leaves, pollen, and animal remains show that Antarctica still had functioning ecosystems during the Paleocene and Eocene, millions of years after the asteroid impact. But the continent was becoming increasingly isolated. Antarctica had once been connected to other pieces of Gondwana. South America remained attached through the region around the Antarctic Peninsula, while Australia was linked along the opposite side. These connections allowed plants and animals to spread between continents, and also blocked ocean water from flowing freely around Antarctica. As those land connections broke apart, the geography of the Southern Ocean changed. Australia moved north. The gap between Antarctica and South America widened. Ocean gateways began opening, although the exact timing and climatic effect of each opening are still debated. This mattered because Antarctica was no longer just a polar continent on a warm planet. It was becoming a polar continent surrounded by water. Water can carry heat toward land, but a continuous current flowing around Antarctica could also help separate it from warmer ocean systems farther north. At the same time, atmospheric carbon dioxide was declining over millions of years. The greenhouse world that had protected Antarctic forests was weakening. The change was not immediate. Forests did not vanish the moment an ocean passage opened, and ice did not suddenly cover the entire continent. Cooling arrived unevenly. Cold-adapted forests survived in some regions while other landscapes became more open. But by the late Eocene, Antarctica was approaching a threshold its forests could not survive. Around 34 million years ago, near the boundary between the Eocene and Oligocene, the cooling crossed that threshold. Carbon dioxide had fallen far enough for snow to survive through summer in Antarctica's interior. Once snow stopped melting completely, it began to accumulate. That changed more than the color of the ground. Fresh snow reflects much of the sunlight that reaches it. Dark soil and vegetation absorb more heat, but expanding snowfields bounce that energy back into the atmosphere. Cooler land preserves more snow, which creates still more cooling. Glaciers formed in high areas, spread into valleys, and gradually joined into a continental ice sheet. The first major ice expansion probably happened quickly in geological terms, but Antarctica did not become the modern frozen continent all at once. Ice advanced and retreated as carbon dioxide, ocean circulation, and Earth's orbit changed. During warmer intervals, forests and tundra could return along some coastal regions. Southern beech trees and low vegetation survived in parts of Antarctica long after large ice sheets first appeared. Eventually, those final plant communities lost ground too. By roughly 14 million years ago, a major cooling step helped establish conditions much closer to modern Antarctica. Ice expanded, sea ice became more persistent, and the continent's interior turned into an extremely cold, dry desert. As ice thickened, it buried valleys, rivers, lakes, soils, and mountain landscapes beneath sheets that now reach several kilometers deep in places. Modern Antarctica is therefore not simply an old continent that has always been frozen. Its ice is a relatively recent cover placed over a much older landscape. Radar surveys have revealed enormous valleys and drainage systems hidden below the ice. Some were carved by rivers before permanent glaciation. Others were reshaped by moving ice. Beneath East Antarctica, researchers have identified preserved terrain that may have remained protected for millions of years, sealed away while the surface above became one of the harshest environments on Earth. That buried world also explains why Antarctica matters far beyond its own history. Its transformation shows that a polar position alone does not guarantee permanent ice. A continent can sit over the South Pole and still carry forests if greenhouse gases, oceans, and winter temperatures allow it. It also shows that large climate changes rarely come from one cause acting alone. Falling carbon dioxide weakened the greenhouse climate. Separating continents reorganized ocean circulation. Snow and ice reflected sunlight and amplified the cooling. Geography prepared the trap, climate pushed the system toward it, and feedbacks helped close it. Before Antarctica froze, it held rainforests, seasonal woodlands, dinosaurs, mammals, giant penguins, rivers, and long polar nights. The ice did not create Antarctica. It hid almost everything Antarctica had been, and survival through that changing world was never guaranteed. To see how another ancient lineage endured a global disaster, watch Why Did Crocodiles Survive? While Other Giants Vanished? Thanks for watching.